Calculus BC, lesson 6.5. We are really proving this trapezoidal rule, what we see in green here. We began to look at some individual trapezoids here. Take a look at what's happening. We've got this old geometric definition, which we're still going to need, even here in BC Calc. The area of a trapezoid is 1/2 base 1 plus base 2 multiplied to the height or the distance between the bases. One thing that I do want to point out to you is each and every one of these areas will have a 1/2 and a delta x. So we could factor that out. And what would that leave us with? Well, an f of x naught plus f of x1 for my first trapezoid. Here's my second trapezoid. Oh, look at this, an f of x1 plus an f of x2. Let's go to our third trapezoid in green. Well, we'd have an f of x2. Oh, another f of x2. Look at that. Plus f of x3, and so on. Well, we're almost done. Remember, delta x was b minus a over n. b minus a over n. If I multiply that by 1/2, I'll have b minus a all over an n, but I'll also have a 2 down there. And wow, look at this. Your f of x1 and f of x1, there are 2 of them. And there are 2 f of x2s. And there'd be 2 f of x3s. And you're going to keep getting doubles of all of these until you get to your very last base here, which is f of x sub n. And I hope this picture right here will show you, look, in blue and in red, this f of x1 was a base for 2 trapezoids, for the blue trapezoid and the red trapezoid. Look at f of x2. It would be a base for the red trapezoid and the green trapezoid. Just like any base here, it's going to be a base for 2 trapezoids, with the exception of your first base and your last base. So that's really what we're getting at, your f of x sub 0 and your f of x sub n. So this is more or less a proof as to what is happening. But again, we are assuming that delta x is constant. As soon as delta x is not constant, we have to resort to just doing the area of trapezoids individually, 1/2 times base 1 plus base 2 multiplied to the height. You can always do that. That's always going to work. It's just that this formula can speed that up a little bit. So let's see where we're going here. It says use the trapezoidal rule for trapezoids to estimate what's happening with this integral. Now, ironically, let's be honest, if we wanted to find what's happening with this integral, we could work it out way quicker by hand, and we could get the exact answer. But we're just dealing with basic premises. I think our next problem can show you why we can appreciate having this method. You can see that if we had n equals 4, we know that delta x is b minus a all over n. So our b is 2 and our a is 1. So we have 2 minus 1 all over a 4. That's just 1/4. So in other words, physically what's happening is we'd go with a 1, then we'd be at 1.25, then we'd be at 1.50, and then we'd be at 1.75, and finally we'd reach 2. And you could see that you would have 4 trapezoids, and this would be a height now, your delta x. It's a 1, here we have a second one, a third, and then a fourth. Well, tell you what, we're just going to follow this basic guideline right here. What's this integral approximately equal to? We'll follow the b minus a. We'll go 2 minus 1 all over a 2 times 4. And then we'll say, well, f of 1, that's my first trapezoid. It's the base that won't show up twice. Then we'll have 2 times f of 1.25. Then we'd say plus 2 times f of 1.5 plus 2 times f of 1.75. And then finally, we'll just say plus f of 2. And guys, at this point, you definitely could finish this up. 2 minus 1 is just a 1. Here you get a 1/8. And, tell you what, we could, just with x squared, really get a lot of help just by plugging this in. You can pretty much see when you plug in a 1, well, you've got f of x. 1 squared, of course, is just going to be a 1. But when we plug in 1.25, well, we'd get 1.25. We're going to square that. Actually, you can also multiply by 2. You can see that's a 3.125. This is just doing some number crunching. Then we'll say 2 times 1.5 squared. That's 4.5. 2 times 1.75 squared. And you just have to be patient as you're working this thing out. You get 6.125 plus, well, you can see just where we're going. Plug in a 2. 2 squared is a 4, and we don't double that one up. Well, now what? Now it's just a matter of being patient and writing all these down. In the brackets, we'd get 1 plus 3.125 plus a 4.5 plus a 6.125 plus a 4. And we're going to multiply by 8 or divide by 8. And you can see it's about 2.343. Or if you wanted to round at the end, you'd get 2.344. So, again, that can seem so silly. The fundamental theorem, of course, can get us that answer quickly, easily. This can almost seem kind of silly for us to even have a method like this. But where we're going next might explain why this trapezoidal rule could be so helpful. Let's take a look at this tabular problem. And we're going to change some things up. Rather than have such an extensive table, let's only go from the 9 here up to 12. And this is data that an observer makes measuring outside temperatures every hour from 9 p.m., 9 at night, to midnight. So at 9, we've got 64, and we can assume this is degrees Fahrenheit. At 9 p.m., it's 64 degrees Fahrenheit. 10 o'clock, it drops a little bit down to 62. At 11, we're at 58, and then at 12 midnight, we're at 55 degrees. And we'd like to use the trapezoidal rule to approximate the average temperature from 9 p.m. to midnight. Well, let's go ahead and take care of business here. The average temperature, look, we're blending in the start of the lesson with this ending. Don't forget the 1 over b minus a. Don't forget the 1 over b minus a. I'm trying to be so emphatic here because this integral right here is what we're going to use the trapezoidal rule for, the trapezoidal approximation. Kids get so focused in with the trapezoidal rule, they can forget the 1 over b minus a out in front. Well, we're going to assume that we do, in fact, have a continuous function. And we're going to integrate from 9 to 12. Let's just say we wanted to do that because we're going from 9 at night to 12 midnight. And that means we have our a is equal to 9 and our b is equal to 12. And, just going back to what we saw earlier, This is where you really want to spend time making sure you've memorized this formula. It can really make life easier. It's what we have in green here, that b minus a all over 2n. And if you ever forget, knowing the proof, that's honestly why I wanted to spend some time and work that out. This b minus a all over 2n could get scary for kids, though, as they begin to work this out. We'll talk through a couple of ways to think through this, because right now you might say, well, how many trapezoids do I have? We'll get to that. But we know if a is equal to 9, we're going to have a start at f of 9. Then we're going to go 2 times f of 10 plus 2 times f of 11 plus f of 12. Now, of course, if we were working this out, if we were going from 9 to 10 to 11 to 12, I think you could see how many trapezoids we'd have. Here's the first height. Here's a second height. And over here, here's a third height. So you could definitely get that information. So that's really a cool way to work the problem out. Sometimes kids will count and they'll say, well, it sure looks, as we're looking through this, that we've got 3 trapezoids. By the way, we do. And kids will say, well, b minus a is going to be 12 minus 9, and down here we've got 2 times 3. And that's all well and good. That's fine. You can do that. By the way, f of 9 is 64. F of 10 is 62, so that's 2 times 62. F of 11 is 58, so I'd go 2 times 58. And f of 12, that's just 55. So we're well on our way. But I want to show you something. 12 minus 9 is actually a 3, and these 3's cancel out. Wow, look at that. You get 1/3. And that's fine. You could definitely work it out this way. But guys, as I said in the proof, there's a reason why I wanted to show you the proof. Look, this is also b minus a all over n. And b minus a over n is delta x. And guess what delta x is going to be? And pardon me, I miswrote this. Delta x was always a 1, wasn't it? Delta x, you can see as you're going from 9 to 10, 10 to 11, and 11 to 12, that's always a 1. So 1/2 times delta x out in front, that's 1/2 times 1. I miscopied this down here. I wrote 1/3. It's 1/2 times 1. It's just 1/2 here. See, these 3's cancel out. You get 1/2. You don't even have to count how many trapezoids you have. You could just use some common sense with delta x to get help. So look, I'm going to go 64 plus 2 times 62 plus 2 times 58 plus 55. And we know that inside here is 359. But when we divide that by 2, take half of that, we're going to get 179.5. And guys, that's what your integral is. That's 179.5. But don't forget, you're really finding the average value of the function. You have to go 1 over b minus a. That's 1 over 12 minus 9. That's a 1/3. So we're going to take this number and divide by 3. And when you do, you'll get 59.833. The units for the average value of a function will always be the same units that f has itself. So what are we seeing? You could use the trapezoidal rule to estimate the integral. But if you're finding the average value of the function, you need that 1 over b minus a out in front. What else are we seeing? I hope to just remind you one more time that b minus a all over 2n, another way you could write it is just say 1/2 delta